For the communications of the RAT Mark I, a point-to-point 5 GHz radio was used to transmit video, telemetry, and driving commands to the rover. These operated over ZMQ and ROS2 based network communication, allowing for efficient and prompt delivery of commands. A 900 MHz SICK radio was also utilized to communicate with a dedicated off-board science payload. The rover was operated with an X52 HOTAS setup, utilizing a custom graphical interface to deliver the driver the necessary information to aid in operation. ROS2 was used as the architectural framework to route messages and packets of commands throughout numerous controllers on board the rover. Different types of controllers were used to actuate the different payloads and systems on board, including O-Drive motor controllers for drive, operated through CAN 2.0, and customized Arduino controllers for the corresponding payloads, such as the excavator as well as the ARM and science modules.
The rover chassis is constructed from aluminium extrusion, allowing for extreme modularity, and clad in aluminium sheet for weatherproofing. The body is supported by a rocker bogie suspension system constructed from lightweight carbon fiber tubes and aluminium joints, which allow for easy disassembly and internal cable routing. The 6 wheels are 3D printed from TPU and are each independently controlled and driven by brushless motors through a 70:1 planetary reduction, providing excellent durability and locomotion performance. An excavator is mounted for regolith collection and rock clearing. A linear actuator powers the lift axis, while tilt is actuated by a custom 3-stage cable-driven reducer.
The arm used for the RAT Mark I is a 5-degree freedom arm that is actuated for the use of 2 linear actuators to allow for easier lifting of 5 kilo loads, a custom in-house designed cycloidal gearbox for rotation of the arm base. Finally, joints 4 and 5 are actuated using a differential drive. The end effector is designed so that each finger is individually moved using a servo. It is capable of lifting 2 kilograms. It has one forward-facing camera and has an RFID attached.
Hi, we're the Space Resources subsystem for the RMIT Rover team, and we had the pleasure of competing in the ARCH 2024 competition, where we were assigned 3 main challenges. These were resource identification, material extraction, and resource processing. For our first objective, resource identification, we were required to identify which of the given regolith samples contained the greatest amount of water per mass. To complete this task, we utilized a conductivity-based water sensor mounted to a custom platform on the rover's arm. For our second objective, material extraction, we created an auger-based system which was also mounted to the rover's arm. This system utilized a sheath surrounding the auger to retain any excavated material. To extract the material from the sample itself, the auger was run in a clockwise direction, with a counterclockwise direction utilized to deposit material into the refinery unit. Now, for our final objective, resource processing, we implemented a standalone refinery unit. This system was designed to continuously mix the regolith utilizing a screw conveyor, while actively heating the housing to melt the ice into water. This water was then filtered through a particulate filter, while the processed regolith was ejected out of the bottom of the conveyor.
Having participated in previous challenges, namely the Australian Rover Challenge 2023 and 2024, we have successfully developed a robust and reliable electrical system. Utilizing LiPo batteries for efficient power delivery and using drive motorboards for voltage and current sensing, electrical-related telemetry was able to be transmitted from the field station to the base station for quick analysis and debugging. Having reviewed our performance in the 2024 ARC competition, we have been working hard to make the necessary changes to place our best foot forward in the Canadian International Rover Challenge.